The number systems. The number systems consists of mainly two big groups. The first one is the real numbers, and the second one is the non-real numbers. And then the real numbers I can divide into natural, whole, integers, rational, irrational. I'm just quickly going to look at them quickly. Right, for the natural numbers, you have a sign that looks like this. It's an N with two stripes, or a double bar at the beginning. What's nice about these signs that I'm going to give you for all of the number systems is that this is universal in all languages. So it doesn't matter in what language I speak. When I write a mathematical paper, and I don't use, because mathematics is mostly numbers, I don't use words to describe the number systems I'm working with, but I use these signs. Then it doesn't matter what language the person who's reading the paper is speaking originally, he can understand my paper. So the natural numbers are the numbers that you start counting in when you are a little child. That's 1, 2, 3, 4, 5, 6, 7. Those are the natural numbers. The whole numbers is that same set. It's just 0, 1, 2, 3, 4, 5. It just includes 0 also. And the sign for that looks exactly like the natural numbers. It just has a little 0 there, which makes perfect sense. Then the integers. I know in some areas, depending on where you're from, it's called integers or integers. Doesn't matter what you use. Integers is made with a Z that has two lines there in the middle, and the integers are also the whole number 0, 1, 2, 3, but then it includes the negative numbers also, which is -1, -2, -3, and so forth to that side also. The rational and irrational numbers. There's a formal definition. The rational numbers are numbers that you can write as a fraction with a over b, where a and b are both natural numbers or integers. And then the b is not 0, because if the b is 0, I can't divide by 0 in mathematics. But I'm going to teach you another method to also look at rational and irrational numbers. And then irrational numbers, the formal definition of that is it's numbers that I can't write as a fraction, so I can't express it as a over b, where a and b is then integers. So if I say 0.1 over 1, that's not valid. It must be like 1 over 2, 2 over 3, something like that. Alright, so the rational numbers, I have a little other thing that I want you to look at. When I look at this as decimal numbers, the rational numbers stop, or they are recurring, and the irrational numbers continue. I'm going to explain that now. First, when you look at your calculator, I just want you to let me just zoom in on the calculator a little bit. When you look at your calculator, there is a little button that has a S and a D with two arrows in between. This changes it from standard form to decimal form. So what I do is I use this button on my calculator, and then I'm going to add any number. Say for instance I have root of 4, and then I press equal. Okay, that's already decimal, so I don't need to press the button. But can you see 2, it stops, so this is rational. If I press 0.5 equal, then it gives me this, which I need to just go and write as a decimal number by pressing this button. And then can you see that this number continues, so this is irrational. Quickly have a look at pi. If I press pi equal, it gives me pi, and I make that a decimal. and this is a number that continues. Obviously on the calculator it stops, but that's because the calculator only has so much space. If I have, say for instance, 3/5, which is a fraction, and I know fractions are rational, but if I have 3/5 and I write that as a decimal number, can you see that it stops? So that is something to consider. Whenever a number, let me just quickly, I think 2/9 is a recurring number. Taking a wild guess, yes. Yeah, can you see that this number continues, but it continues with a little pattern, and because it has this pattern, then I can say that it continues, yes, but specifically, let me just zoom out. Numbers that stop are rational and numbers that continue are irrational, but if it continues with a pattern that I call recurring, those numbers are also rational. So this is like the exception to the rule. So I can very handy use my calculator to identify numbers as rational or irrational. Obviously, if a number is already in a fraction, you know it's rational. But if you are unsure, this is an easy way to test that. And then the real numbers, as I said in the beginning, is all of these number systems. So all of this, the rational and the irrational numbers, are real numbers. How do I get a non-real number? Non-real numbers, when you put them on the calculator, give you a math error. The word may vary from calculator to calculator, but you know when you get an error on your calculator, that is a non-real number. Anything else, if it gives you any answer, then it is real. Then it is a real number, right? So whether it continues or stop or recurring, or it's a whole number or an integer, if there's an answer on your calculator, it's a real number. If it says math error, then you get a non-real number. There are two cases where I get non-real numbers. That is, first of all, when I have a negative underneath a square root. I can't take the square root of a negative number in math, not up until matric anyways. So then I will get a math error, and that's non-real. Or if I divide by 0, then I get a math error. Right, so let's quickly look at this example. I just want to position the camera so that you can see that. I hope you can read all of the numbers, but I'm gonna read them anyways. Let's look at an example to try and identify which of these numbers are then real or not. Right, so the number 10, if I look at the definitions here, if you're unsure, is definitely a natural number, because natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There it is. Yes, and it's definitely an integer, because the integers are all the natural numbers plus the negatives. And then I don't even need to put this in my calculator. I know this stops, because 10 stops, but if you do put it in your calculator, you will see that it stops, and that is then rational, and it doesn't continue, so it's not irrational. And whether it's rational or irrational, it will always be real. If I put 10 in my calculator, 10 is equal to, it does give me an answer. The only way it's not real is if it's a math error. So this is real. Right, then for -6, this is not a natural number, because the natural numbers are only the positive numbers. You will see I didn't include the whole numbers, the one with this one with the 0. I didn't include the whole numbers because it's pretty much the same as this one, it just has the 0 added. And then -6 is indeed an integer, and then -6 stops, so it's rational, it's not irrational, because it doesn't continue. Continue means -6.1324567, it continues. And then if I put -6 in my calculator and press equal, what will happen? It will say -6. So I will get an answer, and that is then real. Alright, this number is 0,6 and it has a little dot there, which means it's recurring. So if I write this number out in full, it will look like this: 0.666666 over again. This is definitely not a natural number, because the natural numbers are the counting numbers 1, 2, 3. I don't count in decimals, and the integers are also numbers that I count in with negatives included, but not decimals. And then this is the special case of rational numbers, so it is rational. All recurring numbers are rational, they're not irrational. By the way, rational and irrational is an either or situation. A number can't be rational and irrational. It's either rational or irrational, apart from when it's not a real number, then it's not rational or irrational, but it can't be both. It can be not any of the two when it's non-real, but it can't be both. Right, and then when I put 0.666 in my calculator, 0.6666666 in my calculator, and I press equal, it gives me a fraction, which is actually per definition then rational. But if I make it a decimal number, you see it makes a 7 there. It's just because the calculator rounds off, a little bit of a smart calculator, like a smartphone. Right, so this is then a recurring number, and there is an answer indeed, so this is indeed real. Right, now the fifth root of 32, I'm guessing quickly, is 2, but I'm just going to check with my calculator. If I put the fifth root of 32, not 2, 32, it gives me 2. Right, it's 2 exactly, and you can see it stops, so I know it's rational already. Now 2 is a natural number, it is an integer, it is rational because it stops. It's not irrational because it does not continue, it stops, and then I got an answer, so this is real. Alright, 1 and 11 over 25, this is a fraction, which is definitely not a natural number and an integer. Now, I know per definition that rational numbers are fractions, so this is supposed to be a rational number, but let's just check with the new method also. If I press in 1 and 11 over 25, I get 36 over 25, which is 1.44. Do you see it stops? So therefore it's rational, and then it's not irrational, definitely not, and there is a valid answer, so this is real. Right, my pen is giving me a little bit of trouble. Let me just see if I can get another pen that writes. Yes, that's fine. Okay, so the next one is root -36. So I'm going to press root -36. And then if I work this out, it gives me a math error. And then the math error forces me to know that this is non-real. Now, since all of these number systems that we've done here, the natural, the whole, the integer, the rational, the irrational, are all real number systems, if I know this is non-real, it's not gonna be any of these. And 6 over 0, I see I've scratched a bit maybe with working here on the board now. 6 over 0, so I said to you over 0 is going to, divided by 0 is going to give you a math error, but just to check, 6 over 0 indeed gives me a math error, so that means it's not a real number, and these are all real number systems, so it is none of these. Alright, and I hope you now have a good idea of how the number systems work. It is worth remembering that all of the number systems that I've done here to just know that they are all real number systems. And then it's also worth to know it's the only way you can get a non-real number is if you get a math error. There's two ways to get that. With a negative under the square root and with a divided by 0 or over 0 in a fraction. That will give me non-real values. Alright, this is important to know for mathematics. You will see there's quite a few places where we use the number systems, and then it's great to be able to express, say for instance I'm rolling a dice, then I want to set the values of the numbers that I'm working with. That will be numbers between 1 and 6, but not any number between 1 and 6, because I can't get a number 2.5 on a dice. It's only the natural numbers that I'm working with between 1 and 6. Or say for instance I'm working with the heights of the students in the class, then the heights will vary probably from about 1.5 meter to about 2.2 meter for very tall people, and then I work with decimal numbers, so I can't say my number systems there is numbers between 1 and 2.2, all the natural numbers, that's just 2. Then I have to specify I'm working with rational numbers, or all the possible real numbers between 1 and 1.5 and 2.2. So there's specific things that I do that I have to know. I see I forgot to give you the signs for these three. Hopefully you know them. But for rational numbers, I don't know what it is with my pens today. For rational numbers, I have a Q with a little stripe there. For irrational numbers, I also have a Q with a little stripe, but then I just put an accent there or a little I there. And for real numbers, it's an R with just two stripes there at the beginning. And there is no sign for non-real numbers, but what you usually do is you just write non and then put the R, non-dash, put the R for non-real numbers. Alright, so that's everything you need to know about number systems.